Okay, so this numerical is nothing different than what we have solved, but only differences in this numerical. So this is a very important numerical because so far in all the numerical steps and how to draw it and all other things we know. So in this case, you will be finding that first we have to convert it into time constant form. So today we are going to see two numericals, and they are very important because in both the cases we will be able to see what is gain margin and what is phase margin, because you are seeing that there are three poles in the denominator. Three poles in the denominator means maximum phase for this Bode plot at omega is equal to infinity, it will go to minus 270 degree. So what all numericals we have seen so far, every time denominator I was giving you two poles, two single poles, and one case I gave you three single pole, but with that I added one single zero. That means every time you are finding that maximum phase could go to minus 180 degree. So never we had seen what is called as omega PC. So two things are very important in the Bode plot, that is omega GC. So where the gain crosses the axis, that is 0 dB axis and falls below, and there is omega PC. Omega PC is where the phase it crosses the minus 180 degree line and falls below. So that I could not show you ever. I could never show you that phase is crossing minus 180 and going below, but in this numerical you will be able to see that. Okay.
Sir, it's visible.
Okay, so let us first convert this given GSHS. So only GS is said, we can say it GSHS. This is very simple. This is 10 divided by S into S plus 1, S plus 5. So first thing what we have to do is you have to take this 5 outside. So that 5 has been taken outside, and 10 divided by 5, that's why 2 is there. Okay, so don't get confused suddenly from 10, how come the 2 is there at the numerator? Because from this denominator S plus 5, we have taken 5 outside. And in this S plus 1, we can take 1 outside, but that hardly makes any change. So if you are taking this 5 outside, so 10 by 5, it becomes 2. That means we have to draw 4 plots. First plot will be 20 log 2. Okay, so that will be a straight line. Second plot will be 1 by S. We know what is that plot. Third plot will be 1 by S plus 1. So this will be a minus 20 dB per decade starting from corner frequency 1. And next plot is also another minus 20 dB per decade line, but that will be having corner frequency of 5. So if I want to show, I will show this how to draw the amplitude table, amplitude plot table. So in the exam also you have to do like this. So in the given transfer function, following factors, so constant k is equal to 2. So numerator 10 was given, that has been divided by 5, so it is 2. So first thing is 20 log 2, so that comes around 6 dB. So there will be a 6 dB parallel line compared to the ground line. Second is pole at origin, that is 1 by S. So they are writing straight line of slope minus 20 dB per decade. It is passing through omega 10 dB point. So it will start at 0.1 comma 20. Next point it will fall to 10. Next point it will fall to 10 comma minus 20. So all these things are static. So 1 by S or 1 by J omega. Starting point is 0.1 comma 20. Next point is 1 comma 0. Next point is 10 comma minus 20. So if you join these three lines, that is actually 1 by S. Next there is 1 by 1 plus S, that is they are writing. So slope is minus 20 dB per decade and starting point is 1 comma 0. So this is omega C1, that means this is corner frequency, first corner frequency. That's why it is called as 1. 1 means 1 radian per second. So starting from point 1 comma 0, you have to draw a line which is minus 20 dB per decade. So which is the next point? Starting point is 1 comma 0, next point is 10 comma minus 20. So if you join these 2 points 1 comma 0 and 10 comma minus 20, you will be getting this line for 1 by S plus 1. And last thing is 1 by 1 plus S by 5. Okay, so what is that line? It will be starting from 5 comma 0. So same thing I'm repeating every day. So same thing is repeated. So it will start from 5 comma 0. What is the next point? Minus 20 dB per decade. So 5 ka ho jayega 50 and 0 will become minus 20. So this point will start at 5 comma 0. So 1 by 1 plus S by 5. So this Bode plot, it will start at 5 comma 0 and it will be up to 50 comma minus 20. So the same numerical we are drawing. So first, second, third, fourth, these 4 Bode plots you have to draw. Now what is there? In this case, you will be finding that there will be four amplitude lines, and there will be phase lines. So phase line is actually a combined graph. Amplitude graph is a different graph. First we draw different graphs and then we combine them. And how to find the resultant amplitude graph. So previously I had shown you one table where we were finding how to draw the plots separately. That means there are four components in the amplitude Bode plot, and how to draw all those four components separately, that was shown. In this table, preparing the table for magnitude plot, that means resultant magnitude plot. So resultant magnitude plot, if you're finding, if I show you the resultant graph, then I think it will be easier for you. So in resultant graph, you will be finding that there are four things separately drawn. So what is the first thing? First thing is this one. Okay, so I think this graph is visible, clear to all of you. So there are four graphs and we have to join all the four graphs together to get the resultant. So this is the 0 dB line, and after that, a little bit darker line, this is called as 20 log K. So 20 log 2, that is 6 dB. So the above line, above parallel line, darker line, this is actually the 20 log 2, or that is the 6 dB line. And this is the starting point. So this graph, okay, below whatever graph you are finding, this graph is the addition of three poles, that is 1 by s into s plus 1 into s plus 5. So if you're doing that, this is the graph for that, 1 by s, s plus 1, s plus 5. How do I know? See that this is starting from 20 dB per decade. Why this graph? Because this is the 1 by s line. Okay, so initially there is only one line. At 0.1 frequency, there is only one line. What is that? 1 by s. It is starting at 0.1 comma 20. And then it is coming up to this point. What is this point? This point is called as 1 by s plus 1. So at this line is coming minus 20 dB per decade, is coming. It can go up to infinity. But suddenly at 1 comma 0, this slope is going to get changed, because at 1 comma 0 there is coming another line, that is 1 by s plus 1, which is also having a slope of minus 20 dB per decade. So you will be finding that there is a slope change. So from 0.1 to 1, it is minus 20 dB per decade, and at 1 you will be finding that this slope is getting changed. So this is actually becoming minus 40 dB per decade. Okay, so 1 comma 0, and next point will be 10 comma minus 40. So this is the 10 comma minus 40 here. So you cannot join it up to 10 comma minus 40. If you are just extending it, you can find it is touching this point. This is actually 10 comma minus 40, but you cannot extend it up to 10 comma minus 40. Why? Because at 5, this point, this is actually 5 radian per second, there is coming another pole. So from 5, this slope is becoming actually minus 60 dB. So there are three regions. Those who are having pen and paper, you can write down. First region is from 0.1 to 1. Okay, what is that slope? That slope is minus 20 dB per decade. And then at 1 comma 0, another pole is getting added with the 1 by s. So initially 1 by s was there, it is there, and with that 1 by s plus 1 is getting added. That means from 1 comma 0, the initial slope of minus 20 dB per decade is becoming minus 40 dB per decade. Okay, and that will extend up to 5. And at 1 by s plus 5, another pole is getting added with that minus 40 dB per decade. That means 0.1 to 1, resultant slope is 20 dB per decade. 1 to 5, the resultant slope is minus 40 dB per decade. And 5 onward, up to infinity, the resultant slope is minus 60 dB per decade. So that is what is written here. Here it is written minus 60 dB per decade from 5 onwards. Here you can find, okay, here in between 1 to 0.1 to 5, the slope is minus 40 dB per decade, and 0.1 to 1, the slope is 20 dB per decade, minus 20 dB per decade. Now I told you there are two processes. First process, you are not adding the 6 dB with the poles. So in this case, below this, so you can find out this is a two parallel line. So this dashed line is actually only the poles. Okay, it is actually the combined resultant of 1 by s into s plus 1 into s plus 5. And that is given actually above shift of 6 dB. Why shift of 6 dB? Because there is a line of 20 log 2, that is 6 dB, which will get added to all the frequencies. So what they have done is, first they have drawn this line, which is 1 by s into s plus 1 into s plus 5. This line is drawn, which is a dashed line. Okay, without k, it is written here without k. That means now if you are adding 6 dB with that, so every point you have to shift above by 6 dB. Every point you have to shift above by 6 dB. Then this is the line. So above dark line, what you are finding, this is actually the resultant graph. Now from there, few things you have to find out, but before that, first only find out what is the gain crossover frequency. So you are finding that gain crossover frequency is coming somewhere here. And how much is this frequency? So this frequency is 1, this frequency is 2. So between 1 and 2, so this is 1.1, 1.2, 1.3. So around 1.5 or so. Okay, so here somewhere around 1.5 or 1.4 is coming the gain crossover frequency. So this we have to remember, that is omega GC. Omega GC is coming to be around 1.5, or here 1.1, 1.2, 1.3, 1.4. So here it is written here, gain crossover frequency is 1.4 radian per second. So this is one thing we can find out from the amplitude plot. And how much is the phase margin? So I told you that whenever you are finding gain crossover frequency, so I request all of you to practice this numerical today itself by using the semi-log graph paper. So whenever it is 1 by 4, 1.4, so this 1.4 you put below. Okay, and you find the phase. So how to find the phase, that also I will tell you. So at 1.4 you will be finding that the phase will be around 165 degree negative. Okay, this is minus 150, here it is coming, and this is actually minus 165. Minus 165 degree phase is above plus 15 degree compared to minus 180. So you can find here the phase line. How to draw this phase line I'll tell you, but before showing you the calculation only, I'm explaining how does it look. But first I have to explain it, and then only I can tell you that how it looks. But anyways, it will look the same way. So what you are finding is the phase line. The phase line is like this, and here there are 3 poles. That is very important thing. Okay, as 3 poles are there, maximum phase is minus 270. You can find here. Okay, so maximum phase it is going to minus 270 because there is no zero. There are 3 first order pole. That means maximum phase at plus infinity will be minus 270. That means there will be a time, or there will be a frequency at which the phase will cross the minus 180 line. And how much is that frequency? It is given here. You can find out. It is called as omega PC. Omega PC is equal to 2.7. So these 2 frequencies you have to put. This 2 you cannot do. At least this frequency omega GC you can put in the phase plot, and you can find out that the phase will be minus 165 at omega GC is equal to 1.4 degree. 1.4 radian per second. Okay, so anyway, so I'm first telling you the answer, because whatever I do, if you are not drawing it, there is no point explaining any of the things. So whenever it is assumed that you will be drawing it, and while you are drawing it, what are the points to take care? Those are the points I'm explaining. So first thing, you have to find the resultant of these 3 poles, and you'll be finding this below graph, which is given by dashed line. First you have to generate this, and next is you have to add 6 dB. That means whatever points are there, so if this point is there, add 6 dB and join this. So here it is the point, add 6 dB, join this. Here there is all the corner frequencies, and add 6 dB to all the things. Okay, so all the corner frequencies you shift above by 6 dB, and then join all the things, all the points. You are going to get the top dark line. This is the second part. After you have got the top dark line, which is the resultant of all 4. What are the 4? Numerator there is a 2, denominator there is a s, s plus 1, s plus 5. All these 4 things together, you are finding the top dark line. And that dark line crosses 0 at which frequency? So we are finding that dark line crosses 0 at frequency 1.4 radian per second. That means omega GC is 1.4 radian per second. Now in the phase formula, you put that 1.4 radian per second, and you will be finding that at 1.4 radian per second at omega GC, system phase will be minus 165 degree. What you have to say is phase margin is found at omega GC, and phase margin is found to be 15 degree above 1.5 plus 1.5. So here it is written very faint, phase margin is plus 15 degree. Okay, so phase margin is plus 15 degree or 15 degree above than minus 180 line. Hence the system is stable from phase margin point of view. Next you are supposed to find gain margin. So for gain margin, you are supposed to find the phase crossover frequency. That means that frequency at which the phase is crossing the minus 180-degree line. Okay, so this will come through drawing only. So you will be getting this point, you will be finding phase at 1, then you will be finding phase at 10, and then if you are joining it, you are going to get this trend. Okay, so from 1 and 10, if you are joining, you will be finding that it is crossing the minus 180-degree line at 2.7 radian per second. Then you have to say that from the image, the phase crossover frequency omega pc is coming to be 2.7 radian per second, and then you shift this point up. Okay, then you are shifting this point up and you are coming to this point, and you are finding that at omega pc the gain of the system is actually negative. Okay, so this top dark one is the resultant thing. So as you had done previously, omega gc you found how much is the phase. Now at omega pc you have to find how much is the gain, and you are finding the gain is actually minus 12 dB. So again I'll repeat the process. First step, you found the resultant amplitude, then you draw the phase, and then you plotted or you dropped this omega gc below on the phase line. Okay, and you are finding that phase at omega gc of 1.4 radian per second, and you are finding that at 1.4 radian per second the system phase is minus 165 degree, which is plus 15 degree or 15 degree above than minus 180 degree line. So what your logic is, at gain crossover phase is positive or phase margin is positive. That means a system is stable. Next step, we are supposed to check at which frequency the phase is crossing the minus 180-degree line. You are finding that frequency is 2.7 radian per second. So that 2.7 radian per second you have to push upward and check how much is the gain. So gain margin is found at phase crossover frequency and phase margin is found at gain crossover frequency. ये दो confusion वाला चीज दिमाग में बिठा के रखो. So WGC you have to plot down and WPC you have to drop up or take up and check how much is the gain. So you are finding that at omega PC 2.7 radian per second system gain is minus 12. That means you can still increase system gain by 12 dB. Still the system will be stable. Stable means the gain will be less than 0. So what we are finding is at omega pc the system gain is actually minus 12. Minus 12 means how much less than 0? It is 12 dB less than 0. That means we can still increase the gain by 12 dB and system still will be stable. Hence we are calling the gain margin to be positive 12 dB. That means how much cushion do I have? I am having a cushion of plus 12 dB. Already if this gain was above, suppose already the gain was plus 5 dB at 2.7 radian per second. Here the gain is minus 12, but I'm just giving you a scenario. When suppose at omega pc you are finding that this resultant amplitude is at the top and you are finding it is at 5. That means gain margin was minus 5. That means you cannot increase the gain anymore, rather you have to reduce. So negative gain margin means system is unstable. But in this case what you are finding is at phase crossover frequency you are finding at 2.7 radian per second system gain is minus 12 dB. That means we are still having the scope to increase the system gain by another 12 dB and still the system will be stable. That means we are finding that gain margin is plus 12 dB. So finally you have to write in a, so you have to make a block here. Okay, so one block here. So they have made two blocks. You have to make one block here and you have to write that system omega GC is equal to 1.4 radian per second. Gain margin at omega GC is plus 15 degree. Omega PC is 2.7 radian per second. And gain margin at omega PC is plus 12 dB. Again, I'll repeat you. You have to write 4 lines in a dabba. Here, first line you have to write omega GC is 1.4 radian per second and phase margin is plus 15 degree. You have found it from the omega GC line. Next, third line you have to write omega PC is 2.7 radian per second and gain margin is plus 12 dB. Finally, conclusion you have to write here in this block only that gain margin is plus 12 dB, phase margin is plus 15 degree. Okay, gain margin and phase margin both are positive. That means system is ultimately stable. So this is the line where The conclusion of the Bode plot or finding from the Bode plot, it comes from here. So last time I'm telling you, 5 lines you have to write. First line, omega GC, 1.4 radian per second. Phase margin, which is found at omega GC, plus 15 degree. Third line, omega PC, 2.7 radian per second. Fourth line, gain margin at omega PC, that is equal to plus 12 dB. Last line, gain margin and phase margin. So gain margin is plus 12 dB, phase margin is plus 15 degree. Both are positive. So as gain margin and phase margin both are positive, this system is inherently stable. And what is the best sweet spot? What is the best input frequency for both gain and phase to be stable? The answer is in between omega GC to omega PC. That means you are inputting any frequency in between 1.4 radian per second to 2.7 radian per second. So this, as per our knowledge, this is the best frequency which will be stably amplified or which will be stably processed by the system. So what is the system bandwidth for stability? Answer is 1.4 radian per second up to 2.7 radian per second. So in between 1.4 radian per second to 2.7 radian per second, you will be finding that both gain margin and phase margin will be positive. What happens to before 1.4 radian per second? Before 1.4 radian per second, you will be finding that phase margin is positive, but you will be finding that system gain is greater than 0 dB. So gain wise, the system is unstable before 1.4 radian per second. Before 1.4 radian per second, you will be finding phase is greater than minus 180. So phase is stable, but gain is greater than 0 dB. So gain is actually unstable before 1.4 radian per second. After 2.7 radian per second, what happens? After 2.7 radian per second, you are finding that gain is very less compared to 0 dB. So gain is stable. So after 2.7, what is 2.7? It is called as phase crossover frequency. Frequency at which the phase crosses the minus 180 degree line and goes below. Minus 180 phase means the instability starts. Okay, so 2.7 radian per second, this is called as omega PC, and at 2.7 before that phase was stable. After 2.7 phase become unstable. So after 2.7 you have to say that system is unstable from phase point of view. Before 1.4 radian per second input frequency, system was unstable from gain point of view. So in between 1.4 and 2.7, the system is stable both from amplitude point of view as well as from phase point of view. Because if you check after 1.4 or before 2.7, gain is negative. Okay, so after 4.7, after 1.4 and 2.7, before 2.7, gain is a negative. Negative gain means stable. And after 1.4 and before 2.7, you are finding the phase is above minus 180. So that means gain is also stable, that is less than 0, and phase is also stable, that is greater than minus 180. So what is the sweet spot? So this system actually we have designed so that we can operate this system stably in between 1.4 to 2.7 radian per second. Okay, so this is what is the significance of gain margin, phase margin, omega GC, omega PC, and system stability. So one thing I did not show you how to calculate the phase of the system. So now I will show you how to calculate the phase of the system. So this is very easy actually. So if you remember, the system was given by 2 by S into, so 2 by S. So 1 by S was there. So 1 by S is having phase of minus 90. And then there was denominator S plus 1. That means 1 by S plus 1. 1 by S plus 1 means minus tan inverse omega. And there was 1 by S plus 5. 1 by S plus 5 means minus tan inverse omega by 5. Okay, so now this is 1 by S. This is 1 by S plus 1. This is 1 by S plus 5. So all these phases you have to calculate for every frequency. So we have calculated for 0.1. So 1 by S will be always having a constant phase of minus 90. So this is actually a frequency independent parameter. That means any frequency you give, 1 by S will be having a phase of minus 90. Why? Because 1 by S, S means j omega. That means 0 plus j omega. That means tan inverse omega by 0. Tan inverse omega by 0 is infinity, and tan inverse infinity is equal to 90 degree. And as this is at the denominator, a minus always comes. So 1 by s means 1 by j omega. 1 by j omega means minus 90 degree. 1 by s square, if I give you 1 by s square, okay, instead of 1 by s I give you 1 by j omega square, or 1 by s square. How much will be this phase? Minus 180 degree. If I give you 1 by j omega cube, how much will be this phase? It is minus 270 degree. This you have to remember. If I give you only j omega s, okay, so there is one zero at the numerator s, this phase will be 90 degree. If I give you a square at the numerator, this will be 180 degree. So it is as simple as that. Okay. So now our transfer function is 2 divided by s into s plus 1 into s plus 5. So for 1 by s, it is minus 90. And other two things, they will be changing their phase from 0 to minus 90. So you are finding that this tan inverse omega, that means 1 by s plus 1, this is also changing from 0 up to minus 90. So at omega infinity, that means very high input frequency, this will become minus 90 degree. Uske aage nahi jayega. Okay, because this is a first order pole. So every first order pole maximum phase it can generate is minus 90. So as there are three first order poles combined at the denominator, that means maximum phase it can go up to is minus 270 degrees. So 10,000 if you put, it will be around minus 269.8. Okay, it will go very close to minus 270, but in your calculation you cannot show it touching minus 270, because at omega is equal to infinity, this will touch minus 270. So this is how the phase is to be drawn. Now I am asking you to insert the omega gc in this thing. Okay, so that one line you have to insert, because after you are drawing the amplitude resultant, you can find out how much is the value of omega gc. Okay, so that you can show here. So between 1 and 10, you have calculated omega gc is equal to 1.4 radian per second. So just you have to create another row in between 1 and 10, and that is a special reading. That is a special reading which is coming from the graph, and all the students should get omega gc at 1.4. That is another thing. So after we come out from control system exam, we first thing we ask, how much was the omega gc, how much was the gain margin. We just tally our answer with our friends. Okay, so if you're drawing it properly, all the students should get omega gc at 1.4 radian per second and omega pc as 2.7 radian per second. थोड़ा बहुत इधर उधर होता है. So 1.4 somebody can get as 1.2, somebody can get as 1.6, but it won't get to 2, or it won't get to 5 radian. No, it cannot happen like that. Okay, so 1.4 can become 1.2, 1.6. That much tolerance is acceptable. So this is about this numerical. So what was the numerical? Numerical was nothing difficult, but only different thing in this numerical was, so just looking at the numerical, you should be able to understand what is the difficulty level I am actually asking. So here it is actually 1 by 10 by s into s plus 5 into s plus 1. Okay, so there are three real poles which are there in this numerical, that is it. Another numerical I will show you in the same way. Is it visible? There is a square in the denominator. Anybody please confirm? Numerical 9.11.4 and
Yes, sir.
9.11.15.
Yes, sir.
Okay, so this 9.11.4 and 15, this is our next topics. So this 9.11.15 we will solve now, and it is also a very big numerical you are finding. And how this numerical is different. So Deepak sir, whatever he has asked you in root locus, or whatever I have seen, as much as I have seen in second OBA, he has actually asked you something. I think one numerical is there. I don't remember which OBA is this. So I think first one. So he has given a big block diagram. He has asked you what will be the value of K for system stability. So actually you are first supposed to find out what is the overall CS by RS. Okay, from the CS by RS, you have to find out what is the system transfer function and characteristic equation. And from that characteristic equation, you have to put a Routh-Hurwitz criteria to find the value of K. So a big block diagram I can give you, and there some value I can give as K. So ये K वाला न्यूमेरिकल तुम लोगों को हमेशा परेशान करेगा in the second order system, in the steady state error finding system, in root locus, in Bode plot, everywhere this K will come. And what is this K? This K is a gain which we can which you can control externally. Okay, this is not a frequency determined gain. So frequency determined, so this GSHs, if I tell you, okay, this GSHs, there is no K here. In this case, K I have mentioned as 4. Okay, so in this case, suppose S you are putting as 10, you will be finding the value of GSHs as something, and S you are putting as 100, that GSHs value will reduce. So whenever I am saying the amplitude of GSHs or overall system gain, that will be a frequency determined gain. This K is not frequency determined. This K is externally we can control. Okay, what we have done in case of root locus. So here, this numerical, whenever we are doing, draw the Bode plot of the system whose open loop transfer function is given by GSHS equal to K divided by S into 1 plus S, 1 plus 0.1 S, 1 plus 0.02 S and all those things. So ये बहुत फिरकी वाला न्यूमेरिकल है, बहुत सारे चीज़ है. Determine the value of K for gain margin of 10 dB. Very important numerical. And just looking at it, can you tell me whether the phase will cross minus 180 line or not cross minus 180 line? Can anybody please answer? GSHS, looking at it, can you just tell me whether the phase, system phase, overall resultant phase will cross 180 minus 180 line or will not cross minus 180 line?
It will
And
not
why?
cross.
It will cross because there are 4 single order poles. Isn't it? There are 4 single order poles. That means maximum phase will be minus 360. What is the phase produced by S? Minus 90. First order. What is the phase produced by 1 plus S? Minus 90. Maximum phase at omega is equal to infinity. अभी जो numerical हम लोगों ने किया, okay, just now whatever numerical you have done, why did it cross this thing? Why did it cross minus 180? Because you are finding there are 3. इसका मतलब तुम लोग सुन नहीं रहे हो. Okay, because you people are very smart people, you can understand it very easily. See this S. What is the maximum for S? Phase for S? Minus 90. S plus 1. What is the maximum phase for S plus 1? Minus करके देखो. Minus tan inverse omega. Omega infinity. How much is the phase? Minus 90. Okay, 1 by S plus 5. Okay, 1 by S plus 5 means minus tan inverse omega by 5. Substitute omega as infinity. You'll be finding phases minus 90. So whenever there are 3 things like this, minus 90, minus 90, minus 90, that means maximum phase can be minus 270. I had shown you that. Okay, I had shown you that maximum phase had gone to minus 270. You can check. Okay, you can check this. You had seen this is the phase. What was the phase? It is touching minus 270. Because there are 3 poles, it is touching minus 270. Now I am asking you same thing. There are 4 single order poles. That means 1 by S minus 90. 1 by 1 plus S minus 90. 1 by 1 plus 0.1 S minus 90. 1 by 1 plus 0.02 S minus 90. So what can be the maximum negative phase at omega is equal to infinity? It will be minus 360 degree. Understandable? Anybody please confirm? Is it understandable that maximum phase can be minus 360? No, nobody? Hello? Nobody understands this? Okay. So Abrar is saying, yes, sir. Anybody else who has understood this? How to find phase? How to find phase? 1 plus 0.1 S. S is equal to j omega. That is the first thing you have to substitute. Okay, first thing you have to substitute, S is equal to j omega. Now just take this part. 1 by 1 plus 0.1 j omega. Okay, so I'm just telling you about 1. Other things will the same thing. So substitute in place of S, substitute j omega. So how to find amplitude, how to find magnitude of this, how to find phase? First thing you have to substitute S is equal to j omega. So if you're substituting j omega, you'll be finding real part is 1 and imaginary part is 0.1 j omega. How much will be the phase of that? 1 by 1 plus 0.1 j omega. It will be minus tan inverse 0.1 omega. Okay, so for the denominator, it is tan inverse imaginary by real. So tan inverse 0.1 omega by 1. That means tan inverse 0.1 omega. And as this is the denominator, when you shift it upward, it will become minus tan inverse 0.1 omega. So phase for this thing is minus tan inverse 0.1 omega. Phase for this thing is minus tan inverse omega. Phase for this s is minus 90. Phase for this 1 plus 0.02s minus tan inverse 0.02 omega. Now you have to substitute omega from 0 to infinity. If you are substituting infinity, that means minus tan inverse infinity. How much is minus tan inverse infinity? Minus को minus ही रखो, tan inverse infinity becomes 90. So for this phase is minus tan inverse 0.02 omega. For this phase is minus tan inverse zero point 0.1 omega. For this phase is minus tan inverse omega. So if you omega tends to infinity, this phase will be minus 90. This phase will be minus 90. This phase will be minus 90. So for all these four poles at omega tends to infinity, the combined phase will be minus 360. That means it will start above minus 180. It will be keep on coming down as omega increases. At omega pc, it will cross minus 180 and come below. And as omega tends to infinity, it will go to minus 360 and settle down there. Okay, now we have to do the Bode plot, and we will find both gain margin as well as phase margin in this numerical. So till last date, if you see whatever numericals I am doing, I am increasing the difficulty level step by step. Okay, initially in case of root locus also we have seen that we have done 2 real pole system, then 3 real pole system, then 4 real pole system, then 1 0 and 4 real pole, then 2 0 and 3 real pole, and finally we had seen what is angle of arrival and angle of departure. So imaginary pole was there as well as imaginary zeros were there. So we will do more numericals on imaginary zero in root locus. In this Bode plot also we are increasing the difficulty level slowly. So initially we had seen only two pole Bode plot. Then we had seen 3 pole and 1 0. 3 pole and 1 0 means for 3 pole phase will be minus 270, and for 1 0 phase will be plus 90. So plus 90 minus 270 is minus 180. So 3 pole 1 0, 2 pole, all the systems you will not find that the system phase is crossing minus 180-degree line and going to imaginary. In that case, what was our argument? At s tends to infinity, the system phase was going to minus 180. What was our argument? The system phase never crosses the minus 180 line and never comes below. So omega pc is not existing. If omega pc does not exist, gain margin is plus infinity. So I think many of you are just keeping your mobile on and you are just listening to it, because I have seen you last 3-4 chapters. You are doing quite smartly, but I think you have lost your spirit, and somehow it is not just clicking. Okay, so just listen to it. The same thing I'm repeating. It is only 2-3 basic fundamentals which are there. There is no very big fundamental there. So every s at the denominator, every first order s at the denominator contributes to minus 90-degree. That you have to remember. So here we will find what is the phase crossover frequency. Here we will find what is the gain crossover frequency. But the biggest problem is the k value is not given. Okay, that means in this case you have to draw only the lines which are produced by, or resultant which will be produced by s, 1 plus s, 1 plus 0.1s and 1 plus 0.02s. So very difficult numerical at your level. Please understand every bit of it, this numerical thoroughly. So I have not given you the k. I have not given you that parallel amplitude which comes at the starting first part. So that actually you have to design. So first you have to find the only the frequency dependent part, their resultant. From there you have to find how much is the omega gc, and then what is asked here, determine the value of k for gain margin of 10 dB. Very important numerical. Let us see. So since k is unknown, we ignore it. Okay, so initially it is converted into time constant form. So very important numerical. It will be uploaded today. Please check, because lecture is being taken now. So lecture video will be found and it will be uploaded today. So k by s into 1 plus s into 1 plus 0.1s. So 0.1s we have to do s by 10. And 1 plus 0.02s. 0.02 means it is 1 by 50. Okay, so there are 4 corner frequencies now. Actually 3 corner frequencies. One is 1-0, another is 10-0, another is 50-0. So you have to draw 4 lines. First line is 1 by s. You have seen every time how to draw 1 by s. So it will start from point 1 comma 20. It will pass through 1 0 and it will come to 10 comma minus 20. So that is 1 by s. 1 by 1 plus s. So it will start from 1 comma 0 with a slope of minus 20 dB per decade. So what is the next point? 10 comma minus 20. Third point is minus 20 dB per decade starting from 10 0. Okay, so how to draw it? One point is 10 0, next point is 100 comma minus 20. If you join that, you'll be finding it's a Bode plot of corner frequency starting from 10. Last corner frequency is 50. So there are three corner frequencies, 1, 10 and 50. So last corner frequency is 50. So what will be the starting point? 50 comma 0. And what will be the end point? End point will be 500 comma minus 20. So this 1 comma 0, it has to be connected with 10 comma minus 20. 10 comma 0, it has to be connected with 100 comma minus 20. 50 comma 0, it has to be connected with 500 comma minus 20. Then you are going to get all the minus 20 dB per decade lines. So it is said below in this, it is said below. So 1 by j omega minus 20 dB line passing through 1 comma 0. 1 by 1 plus s, 1 by 1 plus s by 10, 1 by 1 plus s by 50. All the things are explained here, how to draw the magnitude curve. How to draw the phase? So for 1 by s, it is minus 90. I had explained to you. 1 by 1 plus j omega minus tan inverse omega. 1 by 1 plus j omega by 10 minus tan inverse omega by 10. And 1 by 1 plus j omega by 50 minus tan inverse omega by 50. It's very easy. Bode plot is very easy. Only students are not ready to do the head banging first. Okay, initial head banging, if you do, first give one numerical you understand properly. All the numericals are repetitive. There is nothing different in any of the numericals. So what is the total phase? How much is the total phi? Phi is minus 90 because all the phases are determined by denominator part only. Okay, because numerator it is k, that is having phase of 0 degree. What is the total phase? What is the formula for that? The total phase can be given as minus 90 minus tan inverse omega minus tan inverse omega by 10 minus tan inverse omega by 50. So together, okay, I am showing you now together what is the phase equation. So there will be only one phase equation. So that is minus 90 minus tan inverse omega, that means omega by 1, minus tan inverse omega by 10 minus tan inverse omega by 50. Okay, so just keep on substituting any value of omega, 0.1, 0.2, 0.1. So not necessary to find all these intermediate things, because in your calci you can push this equation and just keep on giving different values of omega, and you can get all these different values. Okay, so one very interesting thing you can find here is 0.1, the phase is positive. Okay, and it is starting from positive. And then 0.2, the phase is coming to be negative, minus 102. And I'm sorry to tell, here is a mistake actually. All these below phases should be negative. Okay, though they have written all the phases as positive, but all these phases actually have to be negative. So I'm sorry, this kind of numerical, so this kind of printing mistakes are there. So all these phases below also you'll be finding they're all negative, and they will be getting added with minus 90. So everything below, okay, everything below is minus 90. And at 1000 radian per second, you'll be finding the phase will be very close to minus 360. So this should be minus 356.49. So this block starting from this 45 up to this 356 and up to 141.8, all this phases should be negative, and all the resultant phases also should be negative. So you are finding that in between 2 to 5, okay, there is a phase crossover frequency. This is 167 and here it is 200.87. So between 2 to 5 the phase cross is happening. And from the amplitude plot, they have found out gain margin to be 20 dB. Okay, so how to find it? It is explained in the next graph. So it is given here. I will be explaining. So this is a little bit difficult numerical. It is not very easy. So this is what you are finding. Okay, so this is the overall resultant graph. This is the overall resultant graph you are finding. Okay, and this is below is the actually the phase graph, and phase graph does not need any k value because k value is constant. Okay, so k value is constant means you are finding that now gain crossover is happening at somewhere here. Gain crossover is happening at somewhere here, and at gain crossover you are finding that phase is around 36 degree above than 180. So here you are finding that in this point, that is gain crossover, which is around 1, you're finding that the phase is around minus 134 degree. Okay, so minus 134 degree is, oh sorry, minus 144 degree, I'm sorry, it is minus 144 degree you're finding here. Okay, so gain crossover omega gc is happening at 1 comma 0, you have to say that, and at 1 comma 0 we are finding that phase is minus 144 degree. So what you have to say is the phase margin is 36 degree. Okay, so the phase margin is 36 degree. And what you're finding is from the graph, the k value does not affect this frequency phase graph, because k is always having a phase is equal to 0. What you're finding is phase margin omega pc. So omega gc is 1 radian per second, it is written here. Omega pc is 2.7 radian per second. And at omega pc 2.7 radian per second, which is somewhere here, okay, this frequency 2.7 radian per second, you push this up and you find how much is the gain here. So you're finding at omega pc 2.7 radian per second, the gain is coming to be around almost minus 20 dB. So it is not minus 20, it is around minus 18. Okay, but okay, they are saying minus 20, so let us take it. So you can very easily find out graphically that at 2.7 radian per second, which is a phase crossover frequency. How could you find it? You have found it by graph. Okay, so you have to find for this 1 radian per second, then maybe 2 radian per second, then maybe 5 radian per second, and you are finding that the phase crossover will happen between 2 and 5. So you graphically you can find out. So as you are finding graphically, that means there will be changes. So you are finding that 2.7 radian per second is the frequency at which the phase is crossing the minus 180 degree line and falling below. So ahead of 2.7 radian per second, the system phase is unstable. Before this 1 radian per second, the system amplitude is unstable. So what is the sweet spot when amplitude and phase both are stable? The answer is in between omega gc to omega pc. So that is 1 radian per second up to 2.7 radian per second. That means only this much part. Okay, so only this much part, that is the sweet spot. That means we are designing the whole system so that it can operate between 1 radian per second up to 2.7 radian per second. So whenever we want to design a system, actually we do reverse. Whenever we want to design a system, we have to see that what is the frequency we want this system to operate with. So we have to see that the lower side of the frequency is omega gc and higher side of the frequency is actually omega pc. So here we are showing you the system and then we are calculating omega gc and omega pc, and then we are saying that sweet spot is in between omega gc omega pc. Actual life में उल्टा होता है. Actual life में first we decide that okay, I want the system to operate between suppose 100 radian per second and 500 radian per second. So we have to design the pole and zero in such a way that pole and zero means we have to decide we have to design the system components in such a way that omega gc comes to be 100 radian per second and omega pc comes to be 500 radian per second. So we have to design the system components accordingly. That is what happens actually in real life. So in this case we are doing reverse. So numerical is given, we just have to solve and tell you the answer. So what we are finding from this, so k is not taken in this. Okay, so k value is not taken. So we are doing this numerical without k only. We are only doing it for 1 by s, 1 plus s, 1 plus s by 10, 1 plus s by 50. Only for the poles, 4 poles, we are trying to find out how much is the gain margin and phase margin. So last 1 minute I will tell you, for all the 4 poles without considering the value of k, we are finding gain crossover rate at 1 0, and at gain crossover when we dropped this frequency below, we found that the phase is minus 144, which is 36 degree above than minus 180. And we are finding graphically that by sketch the phase is crossing minus 180 degree line at 2.7 radian per second, and that frequency we have taken up. How much is the gain at omega pc? We founding that is around minus 20. That means we are still having a plus 20 dB cushion. We can still increase the gain by 20 dB, and then also we are going to get the system as a stable system. Okay, so gain margin is plus 20. Phase margin is plus 36. Hence, we are finding both gain margin and phase margin to be positive. System is stable. Now the question is something different. And what is that? And the question says that what is going to be the values? Okay, so that is the question. What is going to be the value of k, so that we are getting? So just last time, the question I will show you. The question says that determine the value of k for gain margin to be 10 dB. What is the gain margin now? At phase crossover, we are finding that we are having gain margin as minus 20, minus 20 dB gain margin. Sorry, plus 20 dB gain margin we are having. But what they are saying is determine the value of k for the gain margin should be 10 dB. Any answer? Anybody? From whatever understanding you have. That means you can still increase. That means you can still increase the gain by another 10 dB. That means at minus 2.7, at minus 2.7 radian per, sorry, at 2.7 radian per second, whatever we are having, minus 20. As per this numerical, minus 10 bhi chalega. That means whatever resultant is there, you can shift it above by 10 dB more. Okay. So how can you shift above by 10 dB more? That means 20 log x is equal to 10. Okay, 20 log x is equal to 10. Okay, from there you can find what is the value of x. Okay. So if x is 20 log 10 is equal to x, 20 log x is equal to 10. From there just find out what is the value of x. Or you can say 20 log k is equal to 10. How can be the value of k? So this is, so log k is 10 by 20. That means 0.5. Log k is 0.5. You can find what is the value of k from there. So I am finishing this session with this question to you. That is still the question. That is, what should be the value of k? So from this, what should be the value of k, so that you are having a gain margin of plus 10. Here you are having too much good gain margin, plus 20. But मुझे थोड़ा कम भी चलेगा, so plus 10. That means you have to shift this whole resultant graph by 10 dB above. That means you have to add a gain of plus 10 dB. So how much should be the value of k, so that gain will be 10 dB? This is the question, and that is the answer. So what you have to do is 20 log k is equal to 10. From there, find the value of what is k. So log k is equal to 0.5. Find what is the value of k. That is the answer. Fine. So we stop here with today's lecture, and next day 3.16 Amruta. So I'll calculate. So log of 3.16 into 20, that should be equal to 10. Maybe you are correct. Chinmay also 3.16. Very good. So karke dekho, log of 3.16 into 20, does it come to be 10? Log of 3.16 into 20, does it come to 10?
Yes, sir.
Okay, so that is the answer. So that is the value of k. Okay, so you have to say that the value of k, if we are taking as 3.16, in that case we are going to get gain margin of plus 20, plus 10. Okay, can anybody tell me what is better, gain margin of plus 20 or gain margin of plus 10? So those who want, you can leave. Can anybody answer? So bigger the gain margin is better, or smaller the gain margin is better? Gain margin plus infinity is good, or gain margin plus 10 is good? So answer is, bigger the gain margin, it is better. Bigger the gain margin means you are that much below to the zero line. Gain margin is plus 50. That means you are 50 dB below the 0 dB line at omega PC. Okay, what is meant by gain margin plus 20? That means at omega PC phase crossover, you are 20 dB below the 0 dB line. So bigger is the value of gain margin, more positive. Bigger means more positive. That is better. So initially for our case, whatever we did not consider the value of k there, initially the gain margin was plus 20 in this numerical. But what the numerical is asked initially, that I want a gain margin of plus 10. That means you can shift this resultant graph 10 dB higher. That means k value you can keep as 3.16. Okay. So k value, if you are keeping as nothing, the way it is done, k we are not considering, we are getting this is, or k if you are taking as 10, you are finding this. So smaller is the value of gain margin, that is worse. That means you are going towards instability. Bigger is the value of gain margin, positive. That means that is better. That means you are having that much cushion to increase the gain, and still the system will be in a stable region. Anyways, so we will start with, so there's a big caution, we will start with second order Bode plot from next day onwards. So Wednesday, or mostly in tomorrow only, tomorrow's lab session, we will start with second order Bode plot, and there we will require the concept of zeta. Okay, so how to calculate Bode plot with zeta, that is damping factor, that will be shown to you. So please, you attend tomorrow's lab session without fail. We'll start sharp at 10 o'clock, and please be ready with semilog graph paper. So you please today purchase some semilog graph paper and attend tomorrow's session. That's all. Thank you.